Greetings, everyone. Here we have a graph of velocity versus time. And it's important when we're interpreting these graphs that we first of all look and see what it is we're graphing. So we have velocity in meters per second versus time in seconds. And we want to look at what this motion is. Now, up to this point, we've pretty much confined ourselves to looking at slopes and y-intercepts when we are analyzing graphs. But that's not the only things we can look at. Okay, there's also something called the area under the curve. This is the area between the graph and the axis. Now, you may first be wondering, where's the curve? Right? We have straight lines here. Well, remember here that a straight line is really a curve with no curvature. You know, it's kind of like a rectangle is a parallelogram with 4 right angles, or a square is a rectangle with 4 equal sides. Well, a straight line is really just a subset of curves that don't curve. Okay, so area under the curve is the correct terminology, and it's kind of a calculus terminology. So, on some graphs, not all graphs, but on some graphs, the area under the curve actually gives you a physical meaning. So let's see what it gives us here on a velocity time graph. Let's start out by looking at the area under the curve from 0 to 3 seconds. That would be this area. Well, that area is, of course, a rectangle, and hopefully you know how to find the area of a rectangle. It's simply length times width. So, let's take this as the length. Okay, this length is 3 meters per second, and this as the width is 1, 2, 3 seconds. So our area is 3 meters per second times 3 seconds. Now, when we multiply this, the second on the top will cancel out with the second on the bottom, and so we'll be left with positive 9 meters. Well, what does that tell you about the motion of the object? It tells you that the object moved to the right 9 meters. What do you call that? How far something moves and its direction? Well, that is, of course, displacement. So we can see here that the area under the curve of a velocity versus time graph is the displacement, the change in position of the object. Now, this is only, again, for velocity time graphs. If this was a graph of position versus time, the area under the curve doesn't really have a physical meaning. But on a velocity time graph, the area under the curve is always the displacement. So let's look from, and there it is, so displacement is delta x, remember, with an arrow because it's a vector. So let's look at the area under the curve from 3 to 5 seconds. Well, notice what's the velocity? 0, right? We're right on the time axis. And if something isn't moving, it can't change its position. Right? So there is no area between that graph and the axis. So our displacement there is simply 0 meters. Now, let's check out from 5 to 8 meters. That's this area. Okay, that area right there. Again, we have a rectangle, so it's length times width. Let's do this dimension as the length. It's just a good order. This length is not 2, it's negative 2 meters per second. Right? And this is going to give us the displacement. And then it's 1, 2, 3 seconds. So again, the seconds cancel out, and we get a displacement of negative 6 meters. Well, what does that mean? The negative tells you not that it's smaller, but that it's to the left. And so we're moving to the left 6 meters. Again, a displacement. So the area under the curve on a velocity time graph tells you the displacement. Now, we might also be interested in the total displacement. And to do that, we just need to vectorially add our 3 displacements. That seems like a fancy term, vectorial addition, but that really means you're adding with direction. And in 2 dimensions, all we need for directions are positive or negative. So we add up our 3 displacements. First we go 9 meters to the right, then we don't go anywhere, then we go 6 meters to the left for a grand total of positive 3 meters. This means that our little walking man we're going to use momentarily will end up 3 meters to the right from where he starts. Okay, so let's actually see the motion here. Before we do that, we have to be a little careful, because as we just talked about, the area under the curve doesn't tell us where the man started. It tells us how much he's changed his position. Okay, so we only know the change in position, not the initial position. And we lose that piece of information if we only have a velocity time graph. So we don't really know where to start it. Just so that we have a place, let's say he starts at 0. So there he is at 0 position. Now, as we said, he's going to walk to the right 9 meters, and then stop, and then walk to the left 6 meters and end up at 3. So here he goes. There's him walking to the right 9 meters, stopping for 2 seconds, and then walking to the left 6 meters. And you can see here that he's walking backwards, or to the left, if you will, slower than he was walking to the right, because it's only 2 instead of 3. Right? Negative's got nothing to do with it. It's only a 2 instead of a 3 meter per second. So let's watch that one more time. Here he goes, walking to the right at 3 meters per second for 3 seconds, stopping, and then to the left at negative 2 meters per second for 3 seconds. So there's the area under the curve. And again, no calculus is really needed so long as we have nice graphs like this that are linear and, in fact, horizontal. Of course, those of you that have taken enough calculus know that there's some calculus behind this as well, if we actually end up with curves.